morning, ladies and gentlemen. Okay, let me make sure my phone's off. Hope yours is too. So we are almost at the end of our journey here. On Thursday, we'll review the entire course. There will be probably about 3 lecture demonstrations that go over the material of the entire course. There will be cannon and a monkey, there will be sledgehammers, there will be lots to show. And then we have a break for the triple R week. We have a one review session scheduled on Thursday at class time. So exactly 10 days from now, 2 of the GSIs will run a review session in the style of question and answer. They will go over standard multiple choice questions. They'll go over the short answer questions to try to prepare you well for the final that takes place on Wednesday, May 14th. I believe 11:30. It's written on the syllabus. So the exam is will be in the same style as the midterm. There will be 3 hours worth of work for you. But so roughly twice as many questions as you will have seen on the midterm. And again, roughly half of those questions will address the last third of the semester, the chapters that you haven't seen on the previous 2 midterms. So that's chapters 9 through 13. And then the other half will be spread over the entire course. So in that sense, the final will be comprehensive. So, but the format is still the same. 6 rather short answer questions, and then on the order of 40 multiple choice questions. Shouldn't be very difficult, one would hope. You'll be allowed the same notes that you have brought for the first 2 midterms, except the quantity now is 3. So you'll be allowed 3 pieces of paper, standard letter sized, with information on 2 sides in whichever form you wish, again, without any optical instruments to decode them. If the 2 sets of notes that you have prepared for the midterm 1 and 2 worked well for you, bring them on. And then you just need to create 1 more for the last third of the course. Otherwise, it's closed book, and the exam will take place here in Pimentel. So if you guys have any questions about logistics. Now, the last part is throughout this course, we've done the in-class quizzes with clickers. Unfortunately, despite being in the 21st century, technology isn't 100% reliable always. So there are still about 50 students in this class who have participated in the polls but who haven't registered, or at least the software thinks you haven't associated your student ID with the clicker. So the ETS has finally given up on the automatic solutions, so they will be contacting each and every one of you who hasn't associated your name with the clicker on B courses so that we can get that association set up, and the credit for the quizzes can be loaded into the gradebook. In parallel with that, please take a look at the gradebook. There I have posted the most recent summary of the in-class quizzes. They're listed by date, so something like April, last week was whatever it was, say April 24th. So there will be quizzes listed by date. They're scored out of 5 points, 2 points for being in class, 3 points for answering the question correctly. If you know that you have been in the class and you had the clicker activated, but the score shows nothing, that is dash, not even the 0 score, send me your clicker ID. So again, it's in the back of your clicker. We'll do it in parallel with ETS. To be honest, I'm not very confident in ETS's ability to process everything in a week. So if you have been in class and you don't have the credit on gradebook, please let me know, send me your clicker ID, and I'll do it manually. And I'm happy to process 50 of you who still haven't been registered. That said, so any questions about that part of the logistics? So again, I apologize that it has taken the entire semester to get the technology up and running, but I'm assured that as time goes on and B courses is rolled out to every course on Cal campus, it will get better. So we're looking forward to that. So with that in mind, we'll talk about modern, again, we have been talking about modern physics over the past couple of weeks. And so we finally are graduating to look at our entire universe, and we'll actually use some of the knowledge, some of the information that you have gleaned, hopefully, from this course to really look at the world around us and look at it at very macroscopic level. And, in all honesty, humans, curiosity is the very natural human trait. For tens of thousands of years, perhaps since the first humans started walking the earth and able to look up and gaze at the night sky, we've been all wondering, or at least some of us have been wondering, what is the world around us look like and how it's structured and what are those bright objects in the night sky, how they behave, how they work, will they be there tomorrow? If you go out in the city somewhere or go up in the Oakland Hills and it's not very foggy, you can take a chance to look up. Maybe you can see a meteor or two. Maybe you can see a falling star. Meteor showers happen roughly once a year. There's this Perseus meteor shower that happens. It's a beautiful sight. If you're romantic, if you have a special someone with you, that can be a nice experience. If you're scientifically, intellectually, or curiously inclined, you can wonder how this all is put together. And so, poets write poems, artists paint, photographers take pictures, scientists analyze. So we can try to answer the questions about what our place in the universe is, and this is our place. We are really a tiny speck in the overall fabric of the universe, but we can progressively go out of our round dish, not exactly spherical, but close to spherical planet that sits in the local solar system. So this is our solar system that sits in our interstellar neighborhood about 4 light years away from the nearest star, that sits in the Milky Way galaxy that you may in fact see. This is the sign of the Milky Way galaxy seen from Earth. This is the scatter of the scattering of the stars seen from the Earth. When you look kind of this way, edgewise, we can look either in the plane of our galaxy, and then we'll see a relatively dense population of stars. If we happen to see out of the plane of the galaxy, you'll see somewhat less dense population of stars. The spiral galaxy that we live in is called Milky Way, and we see it on the edge of it. And then we can look even further out, realizing that we see it in a collection of the galaxies called the local galactic group, that sits in the Virgo supercluster that's part of the somewhat larger set of galaxies that sits in the middle somewhere, or maybe on the edge. Nobody actually knows. For us, we sit in the middle of the galaxy, or in the universe rather, that's about 14 billion years old and about 90 billion light years in size. For us, of course, we can look left, right, up, down, to and fro. we see an observable universe. In other words, we can go as far as the light can take us, detecting the light from the most distant stars that has traveled to us about 14 billion years. We don't know what's outside of that. Light hasn't traveled that far yet. And so perhaps we are sitting in the center of the universe, perhaps we are sitting on the edge. It really depends on our point of view. But we are sitting in an extremely vast space. So just to set the scales for the vastness of that space, clearly if we are here on Earth, we measure things in the units that are convenient for humans. So, we use the meter stick or 3-foot stick to measure distances that are appropriate to us, since the typical human height is about, 6 feet, I wish. 2 meters or so, meter stick presents an appropriate scale for a human. But of course, when we look at very large distances that are appropriate for the cosmic scales, we need to use something bigger. And so several standard astronomical units are used to describe space in such a way so that we don't have to write numbers with a lot of zeros in them if we go back to sizes of meters. So if we look at our local neighborhood, size of the Earth, we can in principle measure the distances on the Earth scales in units of, say, radius of the Earth or the circumference of the Earth. The circumference of the equator is about 40,000 kilometers. So one could invent a unit that's, one Earth unit of 40,000 kilometers or so. That turns out to be inconvenient, mainly because we are living on this spherical surface and, distances, let's say, circumference is closer to pole or shorter than circumference is closer to equator. So we don't end up describing distances in those scales. Maybe we describe distances in kilometers rather than meters, or miles rather than meters. But when you look at the solar system, of course, it's most natural to describe the distances from the point of view of our relationship to our star. And so we tend to describe distances in astronomical units. This is one astronomical unit is the average distance between us and the sun, which is about 150 million kilometers or 100 million miles or so. So this is, 100 million, 150 million kilometers. That's compared to the typical circumference of the Earth, that's about 40,000 kilometers, is about 40,000 times larger. So here's the model, for example, the not-to-scale model of the solar system. We understand, I think I may have a picture here like this, that our system is our solar system is comprised of a star that provides most of the gravitational attraction that keeps the planets circling around the star or keeps the planets on a elliptical or close to circular orbits. We can understand that there are how many? 1, 2, 3, 4, 5, 6, 7, 8 planets. We were supposed to snip the last one. That's Pluto. This is our solar system. And we measure the typical distances in the solar system relative to the distance between us and our star. We are located here as the planet number 3, third rock from the sun, according to a popular sitcom that was popular 10 years ago, about 100 million miles away. Now, of course, if you look out further, then our solar system really is very far in those units from the nearest other potential solar system. The closest star to us is Proxima Centauri, or Alpha Centauri, is in the constellation of Centauri, which is a Greek mythological creature. is about 4 light years away. So, light year is about 10 to the 16 meters, so about 10 trillion kilometers compared to 150 million kilometers. So that's another, how many? 1 order of magnitude will make it 1 billion, and that's another 3 orders of magnitude, or 4 orders of magnitude above that. So 5 orders of magnitude larger than the typical astronomical unit. So 5 orders of magnitude is 100,000 astronomical units. So once you look at the nearest star, you have to write down numbers with a lot of zeros in order to describe distances. And so instead, we can measure distances in the units of light years, or light seconds or light years, in the units of distance of the units are described in the distance that will take light to travel, or that light will cover in about a year. So it turns out, conveniently, this unit is roughly round. So 10 trillion kilometers, or 10 to the power of 16, 1 with 16 zeros meters, is the unit, is the distance that light will cover in 1 astronomical year, in the amount of time that takes the Earth to travel around the sun once. You also have heard, may have heard another unit called parsec, which is also astronomically derived. It has to do with measuring the distances to the stars by observing how far or how much they shift on the night sky when the Earth travels around the sun. So in the old days, astronomers would measure distances by seeing how far a distant star would shift, let's say between January and May, in half a year. So effectively that would compare the position of the star on the night sky between the point where the Earth is on one side of the sun relative to the other side of the sun. And so if you know the radius, the 1 astronomical unit, the diameter of the Earth's orbit around the sun, and using some relatively simple 8th grade geometry, you can figure out how far the sun is. And the unit of parsec has been invented to signify those distances. That turns out to be a distance of about 3 light years, or roughly 30 trillion kilometers. And so the other way to look at it is parsec is roughly the distance to our nearest star. Alpha Centauri is 4 light years away. 4 light years is close to 3 light years, so the nearest star in those units is roughly parsec away. So those units, therefore, describe the distances between typical stars in a galaxy, in our galaxy Milky Way. We are sitting on the edge of the Milky Way where the stars are not very dense. So the typical distances between the stars in our local neighborhood is about parsec. And of course, on these units, clearly our galaxy is significantly larger than that. So our galaxy can then be measured in multiples of parsec units, so in kiloparsecs. And then if you want to look at the distance between the galaxies, you would measure distances in megaparsecs, in the multiple units of that. So that's another derived unit. Now, how do we know about the universe? Well, obviously we know about the universe by making observations, and we can make observations using the tools that we've discussed before. Telescopes are quite prominent. Telescopes can use either visible light, as invented by Galileo, who invented the first telescope, using lenses. Modern telescopes use combination of lenses, or more often parabolic mirrors, which are easier to make very large size mirrors to be more uniform than lenses. We've discussed that the limit of resolution. Earlier on in the semester, we discussed that the limit with which one can resolve optical pictures is often determined by diffraction, by the wave nature of light. And that resolution limit scales with the size of the optical instrument, with the size of the mirror on the optical instrument. The larger the mirror is, the smaller the spread of the waves is that hits the mirror, and the better the resolution is. So the name of the game in this optical instrument in the astronomy is making optical instruments that are larger and larger, so you can make pictures that are sharper and sharper, and therefore also collect more light over a larger surface area and also peek further into the night sky, further into the universe. One of the things that we've discovered also is that some of the sharpness of the pictures can be limited by the glitter, by the shaking of the air, by the jitter in the atmosphere. So as the light rays penetrate through the atmosphere, they can scatter off of the non-uniformities in the air, either dust, or they may experience rather not a diffraction, but refraction, the change in angle as the rays go through the atmosphere, if there are turbulence or differences in density atmosphere. In the atmosphere, the light rays can scatter. And so that ultimately limits precision of the measurements on the surface. So it's helpful to go outside of the atmosphere to create even better pictures. And so you have seen pictures from the Hubble telescope that look extremely beautiful and breathtaking, that can look at the images of the distant stars and galaxies many, many light years away. And that's done by, again, an optical instrument that circles around the Earth at an altitude of a few hundred miles above the Earth and uses a mirror that's about 2 meters size, limited in this case by how big of an object could be fit into a cargo bay of a space shuttle. So these are all instruments that are working in the visible range. You can also look at radio waves emitted by the distant objects. And so some of the observations can also be done in the radio wave frequencies. So this is an example of, again, parabolic mirror that will reflect radio waves into an antenna sitting in its focus. Radio receivers tend to be larger than optical receivers, again, for the same reason as to improve the resolution, the accuracy with which the radio pictures can be made. The larger the size of this dish, the sharper the picture can be. The fact that the radio frequencies, at radio frequencies, the wavelength is larger than the frequencies or than the wavelengths in the visible light means that the diffractive effects, the effects of the wave nature of light, are more important. So all those instruments, both the radio telescopes and the optical telescopes, and perhaps some of the infrared measurements. Measurements can also be done in the gamma ray, at much higher energy gamma ray spectrum, all telling us about the structure of our surroundings. And so we can peek further and further out and look at both the current structure of the universe nearby and also at the history of the universe as we go further and further in time. The fact that the light takes a finite amount of time to travel over large distances, the fact that the speed of light is finite means that the further out we look in the universe, the further back in time we look. The fact it takes light 1 year to travel over the distance of 1 light year of 10 trillion kilometers means that if we look further out at the distance of, let's say, a megaparsec or a few million light years, means that the light that comes to us from those distances has traveled over millions of years, and so effectively we look backwards in time when we look at those distant objects. And this is what is shown here in terms of the units. Even if you look at our own star, if you look at the sun, technically, we are not looking at its current picture, but we are looking at the picture of the sun about 8 minutes ago. The fact that it takes a finite amount of time for the light to propagate between us and the sun, it means that we're actually looking back in time. We're seeing the image of the sun delayed by about 8 minutes. When we look at the moon, we look at the moon about 1 second ago, at the image of the moon about 1.4 seconds back. That's technically a snapshot, again, going backwards in time. If you look at the more distant objects, of course, we're looking even further back in time. And for example, the cosmic microwave background is the radio waves that come to us from all directions. This hiss that you can hear if you tune your radio station to a frequency of about 100 gigahertz or 100,000 FM. That hiss that you would hear if you had such a radio receiver are remnants of cosmic annihilations, of annihilations between matter and antimatter in the very early universe, and those photons come to us from about 14 billion years ago. So they have traveled about 14 billion light years when they hit our antennas here on Earth. So listening to that cosmic microwave background, therefore, gives us the picture of how the universe looked about 14 billion years ago, about 100,000 years after the cosmic explosion known as the Big Bang. All right, so let's go through this sequence of distances again. Again, as I said, we live in the solar system. Solar system is an example of one of the thousands, if not millions, if not billions, of other solar systems that exist elsewhere, both in our galaxy and the rest of the universe. We'll talk about exoplanets or exosolar planets that have already been discovered and cataloged, including planets that looked very much like our own, or may look very much like our own. Our solar system has how many? 3 plus 3 plus 2, 8 planets. Right, and then there's Pluto that has been declassified. The Earth is about 1 astronomical unit away. Is the planet number 3. There's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And then Pluto that doesn't quite fit. What we know about the solar system and the fact that we have figured out that we live in we continuously travel in a circle around our star is determined by the combination of observations and a very simple set of physics laws. The law of universal gravity derived by Newton in the 17th century, and effectively discovered simultaneously by the 3 astronomers, Nicholas Copernicus, Galileo Galilei, and Johann, I think is Kepler's name. Okay, I have to apologize to Kepler. I don't remember. I haven't met him, so I don't know him by first name. Those set of simple laws, the set of Newton's universal gravitational law that says that the gravity strength falls as the inverse square of distance between the 2 objects, and the simple laws of mechanics. The fact that a quantity called angular momentum is conserved. The fact that the bodies tend to move faster over small when they move over trajectories with small radius, and smaller when they move over trajectories with larger radius. This is the law known as the conservation of angular momentum. This set of simple mechanical laws described in 17th century by Newton lets us generalize the planetary motion. In fact, describes all the bodies in the solar system. We know that all of the bodies in the solar system, if they are gravitationally attracted, gravitationally bound to our sun, they all move on circular trajectories, kind of like this ball moving on a trajectory with the fixed radius. So all of our bodies, all of the bodies in the solar system move over such circular trajectories, or trajectories that are close to circle. Maybe they're called general circular closed trajectory would be called an ellipse. So all of the solar system objects move either on the circle or elliptical trajectories. Ellipse is a trajectory which changes the radius as a function of time, so not continuously round, but something that changes the distance between the sun and the object as a function of time. So these objects come closer to the sun for some part of the trajectory and move further away for the other part of the trajectory. And the motion of the object then can be predicted by a very simple relationship between the mass of the object, the mass of the sun, and the typical distance to the sun. That's the fact that the objects are held on these elliptical trajectories by the gravity, and the gravity only depends on the distance between the two objects and their masses, can make very set of highly accurate predictions for the trajectories. So observing an object once, circling around the Earth once, can let us predict its trajectory for any foreseeable future, basically throughout, over and over again, with the only limitation being the extra perturbations over the trajectory, for example, collisions with other heavenly bodies. All of these predictions have now been highly accurately computed and verified. So planets, of course, are only some examples of heavenly bodies that move on closed trajectories, circular or elliptical trajectories around the sun. They are some of the largest and therefore most visible objects in the solar system, but there are other objects. Comets are example of the icy, typically objects that have perhaps a metallic or rocky core, but primarily surrounded by water ice, that travel on the outskirts of the solar system. Those objects most likely have been captured by our sun as they traveled nearby. And therefore, they travel on the trajectories that are very different from trajectories of most of the planets and most of the asteroids that live in the so-called Kuiper belt, the asteroid belt between Mars and Jupiter. This so this is an example of an elliptical trajectory that's highly non-circular, that has the smallest axis very different from the large axis. So this trajectory on which the comets live changes the distance of their closest approach to the sun is much smaller than the furthest distance from the sun. So these objects travel extremely fast when they come close to the center of the solar system, and then they slow down as the comet travels further out on the outskirts of the solar system. As these comets come closer to the sun, it experiences solar radiation to much greater extent that can vaporize the icy water on the surface of the comet, producing a spectacular tail that reflects the sunlight and producing the beautiful taily pictures. This is an example from the Hale-Bopp comet that I have actually seen in my own naked eyes as I was driving on Highway 5 at some point from Southern California. Produces a spectacular image. So these comets come into our neighborhood periodically. For example, this Halley comet is one of the most famous examples, a comet that comes in close enough to the sun to be visible, perhaps once in roughly 100 years or so, so the next occurrence is 2024. And that's typical period of the rotation for these objects, sort of once in a few generations. Other examples of smaller bodies are asteroids, meteors, and meteorites. These are, again, small pieces of rock, typically. These are small celestial objects. And small, can be relative. These objects live in this asteroid belt between Mars and Jupiter, and then there's another one further out in the solar system. There are some theories about how this set of asteroids have been created. Perhaps they're remnants of a planet that existed in this asteroid belt, but got destroyed early in the solar system life by a cosmic collision. So if that's the case, if that's really the remnant of a planet, the structure of those asteroids is very similar to the structure of the planets. They're rocky, they have metals in them. The largest one is called asteroid Vesta. It's about 500 kilometers across. But then there are also smaller objects, and some of them come to us periodically. If they're kicked out of their normal circular or nearly circular orbit around the sun by a gravitational kick given to them by another planet or by another heavenly body passing nearby, for example, by Jupiter. If Jupiter comes around close enough to some of these asteroids, it may kick them out, or another heavenly body comes close, can kick them out from the circular trajectory, and perturb it enough for these meteorites to come closer to the sun and therefore closer to the Earth as well. That happens periodically. When the asteroid comes into a Earth's atmosphere, burning up hopefully in the atmosphere, it's called a meteorite. When it hits the Earth, you can actually, and you can recover the object, it will be called a meteor. It can produce spectacular images, of course, if the object is large enough to not burn up in the atmosphere, and so if it actually hits the surface, it can produce spectacular explosions as well. I'll come back to the movie in a second. And this brings us back to a discussion of energies in various objects and various types of fuel. Meteors travel at extremely high speeds. Their typical velocity, their typical speed is similar to the orbital speed of the Earth. And that's ranges between 20 and about 30 kilometers a second. So on impact, when the meteorite enters the Earth's atmosphere, it can have the speeds of up to 30 kilometers a second. And at that velocity, a meteor can pack a lot of energy. Its kinetic energy per gram is 20 times larger than a gram of a chemical explosive like TNT. So large enough objects that can weigh a ton or so, can produce very spectacular, very significant explosions. You may have seen, now we live in the internet age of YouTube, the most recent large meteorite hit Chelyabinsk region in Ural Mountains in Russia last year. There was actually another one in the northern Russia, in Murmansk, about 2 months ago, but hasn't made as much of a splash. This particular meteor weighed about, there's a description, weighed about 10 metric tons of about 12, maybe 12 to 13 metric tons, 30,000 pounds by estimates. Those estimates are based on the amount of energy it produced when it exploded. It entered the atmosphere with the speed of about 20 kilometers a second, And this, so, 12 metric tons of rock is an object that's about 10 meters in radius, 20 meters in diameter, or roughly, the size of this building. 20-meter diameter is roughly the width of the stage here in Pimentel. So it's a pretty big, chunk of rock. It exploded in the atmosphere before hitting the ground, splitting into smaller pieces. Some of those pieces have been recovered, and they're as large as about a ton or half a ton of rock. Luckily, it did blow up in the atmosphere, releasing the kinetic energy of about 800 kilotons, which is equivalent to about 80 Hiroshima bombs. So a significant explosion. Luckily, it exploded in the air, and the atmosphere shielded humans from most of that energy. The explosion was still quite significant, with about 1,500 people treated for various injuries, primarily due to broken glass and other damage by shockwave. Now that we live in internet age, you can actually see the images, both of the destructive power of this meteorite and how spectacular it looked when it hit the ground. Those are now available on the interwebs. I'll play a short movie here that shows both the impact of the destruction and the pictures. As it turns out, many people in Russia have dash cameras on the dashboard cameras, so you can see some spectacular images. These are two security cameras, and you can see light from this meteor as it passes by. You can see that flash of light in the sky. That's another image. Here's another image of this object. As it goes by, produces, of course, spectacular view. The sound that you hear, of course, is the engine. It's not the sound the meteor produces. It will produce just a very quick shockwave. And this is what the shockwave impact is in the cities. So windows got broken, some structural damage was produced as well. But this is relatively benign. If that meteor hit the ground, and in the populated area, the destructive power, of course, could have been much more significant, since the energy release is equivalent to about 80 Hiroshima bombs. You may have heard about the Tunguska meteorite, which may or may not have a meteorite, may have been a comet, may have been a UFO, according to some conspiracy theorists, that hit also Siberia in Russia in 1908, I believe, and in a very sparsely populated area produced an explosion. It hit the ground and produced the explosion equivalent to hundreds of nuclear weapons, burned a large area of the forest in the Ural Mountains, luckily not hitting nowhere near the populated areas at the time. So these are the solar objects. These are objects that are traveling around our solar system, either on the circular trajectories like meteors or planets, or on elliptical trajectories. So there are good news and the bad news about the meteors. The good news is that their motion can be very accurately predicted. So every once in a while you may hear on the internet or in the news stories about another meteor detected with 1 in 100 chance of hitting the Earth. And then sometime later that chance would be upgraded to 1 in 1,000, 1 in 10,000, and then you'd hear scientists ruling out a potential for the impact of the meteor on Earth. This is done by observing the trajectory of this object as it travels around the sun, close to our own trajectory around the sun. And so by observing the few points on this trajectory, we can then accurately predict how long this object would take to make one full revolution, and then compute how close it may come in the future to our own planet. This can be done very accurately based on a simple set of physics laws. So that's the good news, that if we observe this object ahead of time, we can actually predict whether there is a significant chance of it hitting our planet or not. It would be difficult to predict exactly where this object would hit, since our rotation around our own axis is much faster than any time scale that's the period of the orbital motion. But at least we can predict whether it will come close enough to Earth to be pulled into Earth's gravity and hit the planet. So that's the good news. The bad news is that there are millions of these objects, and some of them are too small for us to see optically, and so we can track the trajectory of large objects, but it's difficult to track the trajectory of very small objects. This meteor that hit Chelyabinsk hasn't been seen until it entered the atmosphere. It's not large enough object to be tracked reliably by the current optical instruments, but we are building systems of networks of telescopes, both ground-based, and there's a project that tries to build a space-based telescope that would look at the near-Earth objects and perhaps predict with higher accuracy how likely those objects would hit populated areas here on Earth. One of those projects is so-called LSST, or Large Synoptic Space Telescope, I think. It's a telescope built to study the very far regions of the universe and look at the universe expansion. Another goal for it it's built out of about 10-meter diameter mirror and is going to be in operation about 2020. One of the side projects using that telescope is to track small enough objects of roughly this size to provide advance warning for our civilization of any potential impact. So we can also look at other solar systems. If we go out into the universe, there's no reason for us to believe that we are living in a very particularly special place in our solar system. We live somewhere on the outskirts of our solar system, here somewhere, and we are slowly rotating. Well, slowly is a relative term. We are rotating around the rest of the galaxy, around the center of the galaxy, with the speed of about 300 kilometers a second. But on the global scales, that's a relatively slow speed relative to the speed of light and relative to the amount of time it takes us to make one full revolution around the center of our galaxy. So there is no reason for us to believe that we are not sitting in the center of the galaxy, we are not sitting in the center of some galactic cluster. There's no reason for us to believe that our solar system is that special, except for the fact that we live on it. So it would be reasonable to assume that there are other stars that have other solar systems, and so it's also reasonable for us to look for them. Scientists have looked. There's a satellite called Kepler. This is a space telescope built specifically to look for signatures of planets as they orbit around distant stars. And the way Kepler looks for these distant planets is in two ways. One is to look at a shadow of a planet as it passes in front of the star. So you can look from a very large distance, and you can see that when the planet passes between the star and our point of view, between the star and the Earth, a very sensitive optical instrument can notice a shadow created by this planet on the surface of the star. So Kepler looks for faint signals from those planets, looks for the small changes in the star's intensity created by the planet passing in front of it. And then, as it turns out, the other way to look for these distant stars is to look at the small vibrations, small jitter induced by perhaps heavy planets as they rotate around the star. And so Kepler also looks at the small changes in the wavelengths of light emitted by the star due to the jitter induced by the neighboring planets. So Kepler, this mission that is orbiting the Earth, has now discovered over 2,000 planets that exist in other solar systems and has classified them by size and by their composition. So in fact, there's a group here at Berkeley that plays an active role in discoveries of these exosolar planets. Jeff Marcy, one of the professors in the astronomy department, is the leader of the project. So over 2,000 of these bodies have now been discovered. Some of them actually with the small enough mass, smaller than Jupiter, with the masses comparable to the Earth. Some of them living in a region of space comparable to the distance between our Earth and the Sun, where perhaps conditions may be right for extraterrestrial life. There's a so-called Goldilocks region in any solar system, the region where the temperatures are just right for the liquid water to exist, which we believe is one of the requirements for artificial or rather natural life to exist and flourish. This region has to be just far enough from the sun so that the temperature isn't hot for water to boil, but at the same time be close enough compared to, for example, distance like to planets like Mars and Jupiter for the water to exist in liquid form. And so several of these candidates actually now are consistent with being at just about the right distance. So we know that our solar system is not unique in the sense that other solar systems exist, other planets exist, obviously other stars exist elsewhere in our galaxy, and therefore perhaps in other galaxies as well. We haven't seen planets in other galaxies. They're way too far. Most of these planets have been discovered in our own Milky Way. So this is what we know about our Milky Way. We sit here on the outskirts of our galaxy near the, we live in the galaxy known as Milky Way. It's a spiral galaxy, which means that it's the density of stars creates a pattern similar to a spiral. The galaxy is rotating around the center with the typical speeds of about 300 kilometers a second at the distance where the sun is, so relatively slowly. There are billions of stars in the galaxy. Of course, the density nearby, near our sun, is not very, the stars are not very dense where we live. Our nearest star is about 4 light years away, or about parsec away. And the density, of course, is much larger near the center. We believe at the very center of the galaxy there's a dark object known as a black hole, where the gravity is so high as to not allow for the light to escape. But that sits in the very middle. So the space surrounding that black hole is filled with gas, the hydrogen helium gas, and also very bright, very dense stars. Of course, our galaxy is not unique either. If you look further out, there's about 3 million light years away, there's the nearest galaxy to us, Andromeda. Then other galaxies, for example, the spectacular Whirlpool galaxy that has been seen by the Hubble Space Telescope. Some of the galaxies are elliptical, so they basically look like the ball of gas, also slowly rotating around the center rather than this spiral arrangement. And so we can classify these galaxies by distance, by size, by the number of stars. But as it turns out, the studies of the galaxies are important in their own right. We can look at how quickly those galaxies rotate. So one of these guys, Frank Zwicky, a physicist from Caltech, has studied the rotation of the galaxies, the way the galaxies rotate around the center, and how the velocity, the speed of the stars in the galaxy varies with distance. And nominally, this dependence, this relationship between the distance to the star from the center of the galaxy and the speed is highly predictable. I'm looking for this ball that I was swirling over my head. Here it is. Typically, you can figure out that if most of the mass in the galaxy is located in the very center, this is similar to most of the attraction of this ball to the center provided by single string. We can figure out that if most of the mass is located in the center, and so most of the gravitational attraction is provided by a point, by perhaps that black hole, you would figure out that the velocity of the star would be faster, would be larger, if the star is close to the center, if the radius of rotation is small compared to the larger radius. So you can figure out that the farther the star is from the center of the galaxy, the slower it would move on the sky. So Zwicky looked at it, and Zwicky and another astronomer, Vera Rubin, have looked and have mapped out how quickly the stars move in these nearby galaxies relative to their center. As it turns out, they were expecting, if Newton mechanics was right, and if most of the mass of the galaxy was located in the center of the galaxy, they would have expected this velocity to drop with distance. What they measured is that, as it turns out, what they've discovered is that the speed with which the stars rotated around the center remained roughly constant the farther you would look from the center of the galaxy. This was unexpected. The only way to explain that is to postulate that all of the mass of the galaxy is not located exactly in the center, but somehow spread out over the size of the galaxy. But then you can compare that observation with observation of density of light. You know, if you look at our own Milky Way, or if you look at Andromeda, we would notice that the center of the galaxy is much brighter than the periphery. So clearly, there are more stars in the center than on the edges of the galaxy, but that's inconsistent with the rotation of the rotational speed of the galaxies. So that led Zwicky to postulate that there must be some other type of matter that produces gravitational attraction of these stars that are sitting on the edges of the galaxy to the center. He dubbed it dark matter. Dark because we don't see it. If we look at the galaxy, we see sunlight, we see starlight. Most of it comes from the center, very little of it comes from the edges. If this dark matter is distributed more uniformly throughout the galaxy, it clearly is not emitting light, and therefore it's dark. We can see it in some other ways. Very recently, about 5 years ago, a cosmic cataclysmic event has been observed. Well, it happened billions of years ago in the arrangement of galaxies known as the bullet cluster. These are two galaxies that collided some time ago. And as those galaxies collided, the hot gas in the center of the galaxy collided as well. So the two galaxies collided, producing a cosmic explosion. The normal helium and hydrogen gas that it can be visible in the center of the galaxy heated up, produced X-rays. So this red blob here is the picture of that cosmic collision as observed by X-rays emitted from the center of each galaxy where the gas, the amount of gas can be measured. But as it turns out, we can then measure the typical distribution of mass in the galaxy by looking at the picture of the faraway stars behind this cosmic collision using an effect known as gravitational lensing. We can basically see how the images of the faraway stars are imaged as the light passes from that background through the galaxy towards us. And as it turns out, gravity can bend light, and so produce images similar to the images that are produced by optical lenses. And so by looking at the amount of bending of that starlight, we can measure the amount of mass in this galaxy. As it turns out, that measurement tells us that most of the mass is not, in fact, located in the region producing X-rays, is not located in the region where the hot gas is, but there's much more mass outside of that region. And that mass, in fact, is undisturbed when the two galaxies collide. So again, this points out that there's some extra amount of material, extra matter, that does not interact when the two galaxies collide and doesn't produce light. We don't know what it is. It's somewhat embarrassing for physicists to admit that we don't understand what's going on either in our backyard, in our galaxy, or elsewhere in the universe. We attribute this amount of gravitational attraction to an additional substance, and we would call it dark matter, and trying to figure out what this dark matter is, whether it's some kind of particles, subatomic particles that haven't been observed yet, or whether the Einstein's equations of general relativity, or just our description of gravity, is incorrect. What exactly is responsible for this type of gravitational attraction is something that we are trying to understand. Now, there are other interesting objects in the universe. Supernovae are, well, here's a picture of a supernova explosion. Supernovae are stars that have outlived their useful life and have blown up. Over there, so these are massive explosions of the stars that have burned most of their hydrogen fuel. If you look at the evolution of the star throughout its history, the stars produce most of their energy early on by burning hydrogen, by combining hydrogen, producing helium nuclei. As most of the hydrogen burns off, the composition of the star changes from hydrogen to helium. At some point, helium starts burning up. And as the amount of material is reduced in the core of the star collapses under the gravitational attraction. The amount of energy produced by the sun and the amount of external pressure produced by the center can no longer balance the gravitational attraction of all of the mass of the star. The star collapses. In this gravitational collapse, fuels nuclear reactions, nuclear fusion reactions that very quickly produce elements in the periodic table above iron. Normal star evolution burns hydrogen, produces helium, then helium burns, producing heavier elements until about iron, and almost all of the elements above iron in the periodic table are produced in this cosmic explosion known as the supernova explosion. And the rest of the supernova explosion, the high energy released by the quick gravitational collapse, reheating of that residual gas and explosion of the star, scatters all of the elements produced in the nuclear fission throughout the universe. We now observe almost all of these elements in the periodic table here on Earth. And almost all of these elements here on Earth, in particular, all of the elements in the periodic table above iron are produced in the supernova explosions. All of the material that Earth consists of, all of the material that we as humans have picked up, have stardust, have the remnants of the supernova explosions in it. That's a interesting scientific fact, but kind of the romantic fact, as Carl Sagan said, that we are all made of stardust. All of us in our bodies, all of the elements in our bodies are scattered throughout the universe by the supernova explosions and then have accumulated in the solar system and in the planets by gravity. So these are supernova explosions. So these are interesting objects. We can look back into the galaxy and then look back beyond our galaxy and try to understand how the universe came about. And the current understanding is that the universe have been created about 14 billion years ago in the cosmic explosion known as the Big Bang. We don't know what caused the Big Bang. That's the subject of somewhat speculative theories. But we know how the universe evolved after the Big Bang and proceeded through several stages, a very quick period of space expansion known as an inflation. We'll talk about that in a second. Preceded by a relatively slow expansion of the universe produced by the expansion of, caused by the expansion of space due to the energy released in this cosmic Big Bang. This expansion is very similar, conceptually at least, to what happens to the gas when you blow up an explosive. You create a large amount of temperature that causes the molecules to fly out from the epicenter of the explosion at high speeds. Something very similar has been going on in our universe for about 14 billion years, where large amounts of energy released in the Big Bang cause positive pressure that causes now the universe to expand, and have expanded the universe to the sizes of about 90 billion light years across. The total age of the universe, as we now measure it, to be about 14 billion years. Now, how do we know this? The way we know this is by studying the fundamental physics laws of nature. In particular, we study the behavior of gravity over large distances and under either very extreme conditions of very strong gravity that exists only near the surfaces of the black holes, or even gravity that's responsible for motion of our planet around the stars. This theory is now has been summarized by Einstein and is understood as the theory of general relativity that describes the gravitational attraction through distortion of fabric of space-time around the heavy gravitational objects. It's relatively unintuitive, perhaps, for our everyday life theory that says that most of the effect of the gravitational attraction is due to distortion of space. But it has measurable effects. It has the effects that predicts that near the surface of heavy objects that produce high gravitational fields, such as black holes, time, again, if you remember from special relativity, time and space are related to each other, and so the objects that can distort space can distort time as well. And so objects that produce high gravitational fields can slow the clocks down, These are examples of the black holes. The perturbation of space-time, the motion of heavy objects can produce some kind of radiation known as gravitational waves that are similar to a ripple in the fabric of space-time, similar to a ripple caused by a pebble you would throw into a water pond that you would see on the surface of the water. Some of the effects of the general relativity have now been measured. For example, the operation of GPS satellites and GPS receivers is required to take into account the effects of general and special relativity. The clocks running on the satellites have to take into account the small differences in the clock period due to the fact that the gravity on the medium Earth orbit where the GPS satellites are operating is slightly smaller than the gravity we measure here on Earth. But the biggest result, the biggest consequence of the Einstein's theory of general relativity is the prediction that the universe expands. Let me skip that. So our understanding of the universe is based on the Einstein's theory of relativity, but also on this principle that we now know as the cosmological principle that says that there is no reason for us to believe that we live in a special place in the universe, except for the fact that we actually live here. There's no reason for us to believe that we are somehow either in the center of the universe or in somehow very preferred space in the universe. We believe that the universe is exactly the same, at least on average, in all directions. So we can look at the universe in any particular direction. Maybe we have to average over the distribution of stars and galaxies, but the space is uniform and the same everywhere else. And so, therefore, the whole spectrum, and our observations confirm that. And so the whole spectrum of stars and galaxies and galaxy clusters and solar systems and the planets is all produced due to small, tiny fluctuations in the fabric of space-time that have been frozen in space and then created gravitational centers as the universe expanded. So the expansion of the universe is one of the consequences of Einstein's theory of general relativity. In fact, Einstein realized that himself. He wrote a set of equations, and then he figured out that this set of equations did not predict a stable, static universe, and that was counterintuitive and unsatisfying to him. He decided to fudge the equations. As it turns out, he introduced something known as a cosmological constant, a fixed number in his equations that was put in order to produce a universe that appeared static. As it turns out, that was a mistake too. And a Russian mathematician, physicist Friedman, later showed that even with this cosmological universe, the solutions of Einstein's theory of general relativity were unstable and actually produced the universe that had to be dynamic, that had to be either continuously expanding or at some point continuously collapsing. Einstein called this invention of the cosmological constant his biggest blunder, but as it turns out, later observations have actually proved that invention of the single number right. And we'll get back to that in a second. So the way we study the evolution of the universe is by looking at how the distant stars, how the speed with which distant stars fly away from us, how that speed changes as a function of time and distance. We look at the Doppler shift. We look at the change in the wavelengths of light emitted by distant stars and seeing whether that amount of shift, that amount of redshift is larger at larger distances or smaller at larger distances. So this has been known by Hubble. Edwin Hubble in the 1930s has discovered that if you look at further and further stars, their typical spectrum would be shifted further and further towards redder colors. So he looked at the relationship between amount of, basically velocity measured through redshift and the distance, and he showed that it followed a linear dependence, roughly linear dependence. This is known now as the Hubble concept, Hubble law. And one way to understand this is, in fact, not to is to describe the universe as continuously expanding. One way to understand this is to imagine that the universe really is a bubble of space-time, similar to this balloon. And then notice that if I start to blowing the balloon up continuously, the distances between all objects on the sky and all objects between us and the objects on the sky will continuously expand. If you imagine the universe being the surface of a balloon and you increase the size of the balloon, you blow it up from the smaller size to the bigger size, all the distances on the sky will increase automatically. And if the balloon continues to increase in size, all of the distances will continue to increase in size, and all of the stars will continuously be flying away from us. Again, this is easy to demonstrate on a piece of a balloon. If I mark 2 points, 2 dots on this balloon, like this, here they're separated by, say, ½ an inch. And if I increase the size, if I blow the balloon up, to some intermediate scale, the size will increase. The distance between the 2 spots on the surface of the balloon will be larger if the balloon blows up. As I increase the size larger and larger, the distance will continuously increase. So this is the easiest way to, in fact, describe what Edwin Hubble observed, that the universe, the speed with which the universe expands, the speed with which the distances between the stars increase, continuously increasing as a function of distance, and therefore continuously increasing as a function of time. So when we look at this continuous increase in the size between the objects on the sky, we may wonder what will happen ultimately to our fate of our universe. Will it continuously expand? In other words, as the time goes on, we live in this neighborhood here somewhere of about 13 billion years. Oh, I guess we need to go back, right? 13 billion years from the birth of the universe. But when we look at the objects in the night sky, we can try to extrapolate whether the universe will continuously expand and all of the sizes will continuously increase, or whether it will eventually collapse back into the original bubble. Many tools exist in order to study this question. For example, we can look at the cosmic microwave background that has been first discovered in Princeton by Bell Labs scientists. One of our own, George Smoot, has received a Nobel Prize for studying very carefully the density fluctuations in the cosmic microwave background that describes the density of matter in the primordial universe about 100,000 years after the Big Bang. He studied a map of the cosmic sky produced by a COBE satellite that was flying in the early 90s. Now we understand the picture of the universe extremely precisely, and we can map out these fluctuations in temperature, in the density on the cosmic microwave background extremely precisely. And we now understand that these density fluctuations, these regions of hot and cold matter, have now been reborn in our current universe 14 billion years later as matter fluctuations, as stars and galaxies. Another physicist in our department, another one of our own, Saul Perlmutter, studied the evolution of the supernova in the nearby galaxies, measuring the amount of redshift as a function of brightness of the stars, trying to map out whether the universe would continuously expand or eventually collapse, trying to study the speed with which the universe expanded as a function of time. And he has shown, in fact, that the universe is, in fact, continuously expanding, and that expansion might, in fact, accelerate with time. We now understand this as something that fuels this continuous expansion. There's some kind of an energy source that fuels the continuous expansion of the universe, known as the dark energy. since we are almost out of time, let me show you some of the open questions that we don't understand about the universe. We know we are made out of molecules. We know we are made out of atoms. We understand those atoms come from the supernova explosions, but we can only account for about 5% of the mass of the universe. All of the atoms, molecules, stars, and the galaxies in our night sky account for only about 5% of the universe's mass, and the rest of it comes in this dark form that does not produce light. It's called either dark energy and dark matter, and what this is, whether it's new forces or new particles, needs to be understood and is subject of intense scrutiny and research now. We don't know if the universe is finite. We also don't know if the universe is unique. There are some theories that predict that the entire space is filled with 10 to the 500 little universes, each with its own set of physics laws. We don't know whether that's true or not. We would like to find out. And as it turns out, the fact that we live in 3 spatial dimensions is not necessarily a given. There may be more. And again, some theories of physics predict that we live in a 10-dimensional universe, but we can only see 3 of them because the rest of the dimensions are so tiny we don't notice them until we look at the very microscopic behavior of matter. Whether that's true or not, perhaps we'll find out in the next 100 years or so. So you might tell about this to your grandparents. So stay tuned. Again, I'll wish you good luck on the exam. On Thursday, we'll review the entire course with the appropriate number of lecture demonstrations and wrap it all up. Thank you very much, and I'll see you on Thursday.